Okay, this is lesson 5.7, cosine law. In this video, we're going to go through and review how to use the cosine law to solve for sides or angles in triangles. Also going to introduce direction and bearing. And we're going to use cosine law in a direction or bearing question on the back. If you're given a triangle where you have a contained angle, and the two sides that contain it, or all three sides, you can use the cosine law to determine the unknown sides or angles. Cosine law will always give you a unique solution because cos never produces more than one angle within the domain of 0 to 180 degrees, like sine law does. Sine law gave you two different angles, or could give you two different angles that give you the same ratio. Cosine law, according to Castro, is positive or negative in the second quadrant, so we can't have two solutions. So it's nice, we only have to consider one case. The other quadrant in which cosine gives you a positive ratio is the fourth quadrant, but angles between 270 and 360 are too big to be in a triangle, so we don't have to worry. So the cosine law, written to solve for a side, looks like this. A squared equals b squared plus c squared minus 2bc cos A. And the way this sets up is to use this equation, you need to have two sides, b and c, and the angle, A, which is the angle between sides B and C. That's why it's called a contained angle. And that'll allow you to solve for side A, the opposite side. If you rearrange the equation and you know all three sides, you can solve for any angle. And we'll do an example like that too. So let's take a look at two examples. Sketch and solve each triangle using cosine law. Round to the nearest tenth if necessary. In triangle XYZ, X is 19.4 centimeters, Y is 14.3 centimeters, and Z is 68.2 degrees. So let's give this a shot. XYZ. I'm going to put the angle I know down here, so I'm going to draw my triangle like this. And Z is 68.2 degrees. We'll call that Z, and we'll call this one X, and this one Y. So side X would be down here, 19.4 centimeters, and Y would be over here, 14.3 centimeters. All right, and as you can see, we have a contained angle. 68.2 degrees is given to us, and it's contained by two side lengths that we know. So we can write a cosine law to solve for side Z. So we got to use the letters X, Y, Z. So we're going to pattern it after the cosine law. So if we want to solve for Z or Z, we need to know angle Z. So our cosine law would start by looking like Z squared equals and then we use the other two sides we know, X and Y. X squared plus Y squared, and then minus 2, and the same two sides we used on the right side. Minus 2xy cos the angle we know, which is Z. And now we have a cosine law. That Z didn't show up very well. All right, and now we can fill in what we know. We know that X is 19.4, Y is 14.3, minus 2 times 19.4 times 14.3 cos 68.2. And now to solve the cosine law, what I would suggest is either two steps. You can either type in the entire right side into your calculator and get a single answer, and that would save any bad math problems. Alternatively, you have to do 19.4 squared plus 14.3 squared, write an answer. Do negative 2 times 19.4 times 14.3 times cos 68.2, write an answer, and then subtract the two answers, or add the two answers depending on the sign in the middle. And then come up with a single number, and the last step is to square root. So I'm going to demonstrate typing the whole thing in. 19.4 squared plus 14.3 squared minus 2 times 19.4, 14.3. Cos, make sure you're in degree mode, 68.2. And we should get 374.8002701. I'm just going to go with 0.8. So we got 374.8. And our last step to solve for z is to square root. And if we square root, we end up with 19.4 centimeters. Now, coincidentally, that's the exact same measure as angle or side x, which is kind of nice if you're asked to solve the triangle, because if you have two sides that are the same length, that means the angles they're across from are the same measure. So if angle z is 68.2 and side z is 19.4, then angle x must also be 68.2 because side x is 19.4. And if this happens to you, you don't even have to solve. You don't have to use cosine law again. You can just draw the conclusion that angle x must be 68.2 degrees. And you can save yourself a little bit of work because now we solved the triangle. Because we know that the total should be 180 degrees. And if we have two angles that are 68.2, we just have to subtract them. And that will tell us angle y, 43.6. And now you've solved the triangle. All right, how do you use cosine law to solve for an angle? Well, let's take a look here. In triangle ABC, A is 38.4 meters, B is 25.2 meters, and C is 19.3 meters. So I'm going to draw an ABC triangle. A, B, C. All we really know is the scale of the side lengths, but I'm not really using a scale here. I'm just kind of drawing them all the same length, which your drawings don't have to be to scale, so it's okay. We've got all three sides. Now, when you have all three sides, you can solve for any angle. And whichever angle you want to solve for, you'd use the version of the cosine law that has that angle. And I'm going to show you how to rearrange it. So let's start by solving for angle A. Angle A would come from the cosine law that's exactly written on the page. A squared equals B squared plus C squared minus 2BC cos A. So how do we rearrange this? Well, we start by moving the b squared and the c squared to the other side, making them negative b squared and negative c squared. So we get a squared minus b squared minus c squared. And that would be equal to negative 2bc cos A. So another step, we want to divide away everything in front of cos A. So we're going to divide both sides by negative 2bc. And that leaves us with cos A is equal to a squared minus b squared minus c squared over negative 2bc. And we could simplify the signs, but we don't really need to. We can just keep it written like this. And this is enough rearranging. If you want to take it one step further, you could cos inverse both sides, and that might actually make it a little bit easier. Now you have something isolated for A. So if we plug in our sides A, B, and C, we can plug it directly into our calculator and solve. So I'm going to replace my letters. A squared would be 38.4 squared. B squared, 25.2 squared. And C squared, 19.3 squared. Run out of room here. Over negative 2, B is 25.2, and C is 19.3. And if we type that whole thing in our calculator, we should end up with the answer. So let's give it a shot. second cos 38.4 squared minus 25.2 squared minus 19.3 squared over negative 2, 25.2, 19.3. And we get 118.7 degrees. So that's the example of doing cosine law to solve for an angle. What I'm going to suggest that you do is try cosine law one more time to find angle B, and then subtract from 360 or subtract from 180 to find your last angle C. I'm going to write the answers here so when you check it, you know whether you got it right. When you do B, you should get 35.1. If instead you choose to solve for C, C should be 26.2. So give it a shot and see what you can come up with. All right, direction and bearing. Direction is always stated as a number of degrees east or west of north or south, and that sounds a little confusing, so I'm going to show you what I mean. Bearing is the direction you have to move in order to reach an object, and it's always clockwise from north. So here's a couple examples. What is the direction from point O to A, B, C, and D? Well, O is right here. And you always start writing a direction by whether the point is closer to north or south. So in the case of point A, it's closer to north than it is to south because it's going up. So we start by writing A is north, and then you state how many degrees towards east or west we're moving. And in this case, A is 30 degrees towards the east. So we would write north 30 degrees east. And that would be our bearing. Sorry, our direction. B. B is also closer to north because we have to go up to get to it. So we start with saying north. And in this case, we're going towards the west. And we're going 60 degrees towards the west. So we have north 60 degrees west. C and D are pointed down. D is down and C is down. So both of those are going to be pointed towards the south. And from south, C is 70 degrees towards the east. So you have south 70 degrees east. And D is south, but 80 degrees towards the west. Now, the only time we don't use the degree is if you're pointed directly north, east, south, or west. If that's the case, you just say north, south, east, or west. Bearing's a little different. Bearing, you always use your measurement from north. So in the case of O to P, we're looking from the origin to point P. Well, from the origin, if we go straight north, we would have to rotate 65 degrees to get to P. So the bearing of O to P is just 65 degrees. O to Q, from O directly north, we would have to rotate all the way around, and it's always in a clockwise manner. And that would take us 300 degrees around until we got to Q. So O to Q is 300 degrees. Where it gets challenging is if the point you have is not pointed towards true north. So if you're not at the origin. So let's say we're trying to go from P to O. If the point you're looking to find bearing from doesn't have north drawn onto it, like P to O, since we're starting from P, we're going to have to draw on where north, south, west, and east would be. And then we have to consider the angle we're actually rotating from north? Well, from north we'd be rotating here to get to the line that takes you to O. And to find the angle that's represented there, you might have to use some of your patterning. So east and west lines, north and south lines will always run parallel with each other. And if you take a look, here's a backwards Z. So there's kind of a Z pattern that we can use to figure out what this angle would be. In fact, from north to our line to this south line, there's also a Z pattern, which tells us that if the angle 65 is in this part, then the angle 65 would be in that part too. And that's going to help us find our bearing, because from north, if we travel around 180 degrees, that takes us to south. 65 more would get us to our line from P to O. And that would be a 245 degree bearing. You can solve the Q to O the exact same way, and I'm actually going to leave that one up to you. I want you to try to come up with the bearing from Q to O. Make sure you check it on the course website when you're done. All right, let's flip it over. So on the back we got two questions. Two boats leave a dock at the same time and two ships leave a harbor. The two boats leaving the dock is the easier of the two, so I'm going to leave that one for you to try on your own, and we're going to do the two ships leave a harbor. So we're going to try to break this down, and there's some more thinking practice below if you want to try that. But two ships leaving a harbor, the first at 12 and the second at 12:30. The first ship sails on a course of north 30 degrees east at a speed of 20 kilometers an hour, and the second ship sails on a course of south 20 degrees east at 15 degrees Celsius. Determine the distance between the two ships. So we're going to start by drawing a diagram, and we're going to start by placing our harbor. And we can place a harbor anywhere. I'm just going to put it as a dot here in the middle. And I label it H. Now from H, I'm going to show the direction the two ships are going. The first ship is going north 30 degrees east. So from the harbor, I'm going to label north. And label south. And I'm going to leave that there. I'm not going to put east and west on. We know east is this direction, west is that direction. North 30 degrees east is the direction of the first boat. So here's my boat travel line. We don't know how far it goes, but we do know that it travels at 30 degrees east from north. The second ship goes south 20 degrees east. So instead of going directly south, we're traveling 20 degrees east. Let's say that this is the end destination of boat A, and this is the end destination of boat B. We want to determine the distance between the two ships at 2:30. Now, if the first ship left at 12, it's been traveling for 2.5 hours. So ship A, or the first ship, was traveling for 2.5 hours, and it travels at 20 kilometers an hour. So the first ship traveled 50 kilometers. So I'm going to add that to my diagram, 50 kilometers. And the second ship left at 12:30, so it only traveled for 2 hours. And it travels at 15 kilometers per hour, which would be 30 kilometers. I'll try to get that on my diagram as well. Now we want to know the distance between the ships, so we want to know this distance. So, to find that distance, we could use the Pythagorean theorem. Not the Pythagorean theorem, the cosine law. Because we know two sides, and we can find the angle that's contained by them. How can we find the angle that's contained by them? Well, let's call it angle H. We can find angle H because we know 180 degrees should be the bearing from north to south. And if we've used 30 degrees to travel a little east from north and 20 degrees to travel a little east from south, the remaining would be 180 minus those two angles, which is 130 degrees. Now, to find x, we can use the cosine law. And we'd have to set it up like this. X squared would equal the two sides squared. So we know 50 squared plus 30 squared minus 2 times 50 times 30 cos, and the angle that's contained is 130 degrees. Our last step is going to be to square root it, so I'm going to do this cosine law all in one step. Now let's see if I can type this in my calculator. So we're going to square root, not third root, square root 50 squared plus 30 squared minus 2 times 50 times 30 cos 130. And I get 72.995, so I'm going to call it 73 kilometers. And that's how we can draw a diagram and use cosine law. Part B asks us to determine the radar bearing from the first ship to the second ship. That's a very challenging question. It would be like a thinking style question. I'm going to leave that to you, but I will tell you that the answer to B is 192 degrees. So see if you can come up with that, and if you can't, we'll actually try to do it in class tomorrow. But that's it for our last lesson. Thanks for watching, and I'll see you next time.